Think of the simplest light you know, an incandescent bulb. If you could touch it, you would feel the heat, a direct conversion of energy into warmth and light contained in a fragile glass sphere. It's a quiet, gentle process. Now let's take that simple principle and throw it into the most violent place in the universe. Imagine not a filament, but a river of gas wider than a star system, swirling into a point of infinite darkness. As it falls, this river doesn't just get warm. It is crushed, sheared, and twisted by gravity so extreme that it ignites. This is the great paradox of the cosmos. The darkest objects imaginable wear crowns of the most brilliant fire, a light born not from burning, but from falling. This structure is called an accretion disk. The concept is as familiar as water circling a drain, but the reality is far stranger. It is a vast, flat whirlpool of gas, dust, and the shredded remains of stars, all caught in a gravitational field they cannot escape. It spins, and as it spins, the inner parts move impossibly fast, a significant fraction of the speed of light. These disks come in all sizes. Around a small black hole, just a few times the mass of our sun, the blazing inner edge might only be 100 kilometers across. But around a supermassive giant, like the one powering the galaxy M87, the disk can span light years. A structure so vast our entire solar system would be a tiny speck within it. So how does this falling gas catch fire? It isn't friction in the way we think of it, like rubbing two hands together for warmth. The gas particles rarely touch. Instead, the inferno is lit by two invisible forces, turbulence and magnetism. Powerful magnetic fields, threading through the gas like unseen wires, get twisted and tangled by the disk's rotation. This immense magnetic tension shears the gas, generating heat. At the same time, layers of the disk moving at different speeds create cosmic turbulence, a chaotic stirring that adds to the blaze. It is friction without touching, a phantom heat that makes the outer parts of the disk glow at 10,000 degrees, shining in brilliant blue and ultraviolet light. As we move deeper into the whirlpool, the oven roars. Closer to the edge, the gas is superheated to millions of degrees, hot enough to flood its surroundings with X-rays. But there's another layer to this hellscape. Floating above the main disk is a ghostly, transparent veil of even hotter gas, a region known as the corona. Here, temperatures can reach a staggering 1 billion degrees. This corona crackles and spits out the most energetic light of all, hard X-rays, like a constant, violent lightning storm raging above a sea of fire. There is a boundary near the black hole, a point of no return for stable orbits. Astronomers call it the innermost stable circular orbit, or the ISCO. Think of it as the last lane on a cosmic racetrack. On this track, you can circle forever, but if you stray one step inside it, the pavement gives way. There are no more stable paths. Any orbit unravels, and you are forced into a final, inescapable plunge. For a black hole of 10 solar masses, this final, stable racetrack is about 90 kilometers from the center. It is here, right on this precipice, that matter moves at its fastest and shines its brightest. We have seen this racetrack in action. At the heart of our own Milky Way, the supermassive black hole Sagittarius A star is orbited by superheated clumps of gas. In 2018, the gravity instrument watched these infrared hotspots as they whipped around the abyss. They completed a full orbit in as little as 30 to 45 minutes. An entire lap around a monster 4 million times the mass of the sun, finished in less time than it takes to watch a sitcom. They were moving at nearly 30% the speed of light, a final frantic dance on the edge of oblivion. For decades, this was all theory and indirect evidence. Then, in 2019, we saw it. The Event Horizon Telescope, an array of radio dishes spanning the entire globe, gave us our first direct look at a black hole's silhouette, the monster in the galaxy M87. It was a perfect ring of light encircling a circle of pure darkness. And crucially, the ring wasn't uniform. One side was distinctly brighter than the other. This wasn't an imperfection. It was the fingerprint of extreme physics. The side of the disk spinning towards us has its light focused and brightened by relativistic effects, a phenomenon called beaming. The side spinning away is dimmed. We were seeing the speed. That ring we see is even stranger than it looks. It's not just a picture of the glowing gas disk itself. It is an image made of light that has been profoundly bent by the black hole's gravity. Light from the gas is warped, and photons from the far side of the disk can be looped over the top and bottom of the black hole before arriving at our telescopes. The bright circle is a photon ring, a gravitational echo. The dark patch it surrounds is the shadow, the region where gravity is so strong that any light entering it is captured, unable to escape. 3 years later, in 2022, the same team gave us an image of our own galaxy's heart, Sagittarius A star. Blurrier and changing faster, but showing the same fundamental truth: darkness wrapped in light. To get even closer, we can listen to the light. X-ray telescopes can detect a specific color of X-ray emitted by hot iron atoms, known as the iron K alpha line. Normally, this is a sharp, precise signal. But near a black hole, that signal is tortured. The immense gravity steals energy from the light, stretching it to redder wavelengths. The incredible orbital speed smears it out. What should be a clean note becomes a broad, distorted cry, the scream of iron atoms being stretched on the rack of space-time. By studying the shape of this scream, we can measure just how close the iron is to the event horizon, and even how fast the black hole itself is spinning. We can even use the light to map the area in a way that feels like science fiction. When the corona above the disk flashes, it sends X-rays down onto the disk's surface. That light reflects off, but the echo from the far side takes slightly longer to reach us than the echo from the near side. By precisely timing these tiny delays, a technique called reverberation mapping, astronomers can build a rough map of the disk's geometry. It is like clapping your hands in a dark, unknown cave and building a picture of the room just from the echoes that return. We are echolocating the very edge of an event horizon. These accretion disks are, pound for pound, the most efficient engines in the known universe. When a star like our Sun fuses hydrogen into helium, it converts only about 0.7% of the mass into energy. It's powerful, but it's not very efficient. Now consider matter falling into a black hole. For a non-spinning black hole, the process converts about 6% of the matter's mass into pure radiation. But for a rapidly spinning one, that number can soar to an astonishing 40%. One spoonful of gas falling into a spinning black hole can release more energy than burning thousands of tons of nuclear fuel. This is why quasars, the brightest objects in the universe, exist. They are powered not by stars, but by these hyper-efficient engines of gravity. The same physics plays out on smaller scales right here in our own galaxy. Take Cygnus X-1, one of the first black holes ever identified. It's a stellar mass black hole, about 21 times the mass of our Sun, locked in a dance with a giant blue star. It constantly siphons gas from its partner, feeding a small but intensely hot accretion disk that glows steadily in X-rays, a stellar vampire humming with power. Others, called microquasars, flicker violently and spit out narrow jets of plasma that appear to move faster than light. They are perfect miniature laboratories for studying the monster engines we see in the distant universe. And sometimes, a dormant giant gets a sudden, violent meal. If a star wanders too close to a supermassive black hole, the immense tidal forces will stretch it, noodle it, and tear it apart. This is a tidal disruption event. The star's debris doesn't fall in neatly. It swings around the black hole, colliding with itself and forming a bright, temporary accretion disk. For weeks or months, The dark center of a galaxy can blaze with the light of the star's final moments, a flare of X-rays and ultraviolet light that marks a stellar death scream. There is a final, strange truth about this place. What you see depends entirely on where you stand. From our safe distance, watching a clump of gas approach the event horizon, we would see something bizarre. It would seem to slow down, its light shifting redder and growing dimmer, until it appeared to freeze at the edge, fading into nothing over an infinite stretch of time. But for the clump of gas itself, there is no slowing down, no pause at the edge. In its own frame of reference, it crosses the horizon in an instant, plunging into the singularity. Two profoundly different realities, both true at once, separated by the warped fabric of space-time. We journey to these places not with spacecraft, but with mathematics, telescopes, and our own curiosity. It's a calm walk through the wildest landscapes imaginable. If you find a sense of quiet wonder in these explorations, consider subscribing to Stardraft. We are dedicated to these deep dives, one cosmic phenomenon at a time. So step back and take in the whole, impossible picture. An engine made not of metal or fire, but of warped space in falling time. A place that creates the brightest lights in the universe out of the deepest darkness. Every grain of sand, every wisp of gas, gives up its final energy in a blaze that outshines the stars themselves, right before vanishing forever. Our own sun will never know such a fate. It will die in a quiet fade, its embers cooling over eons. It will never wear a crown of fire. And knowing that makes the gentle, ordinary daylight of our own small world feel all the more precious.